Six. I didn't get it. I'm just looking Okay, so let's go ahead and begin. So today we're going to talk about a few things. First of all, and I put the page from the assembly language manual on every table. It's the page that has the alternative names to the reg file register. So we're going to talk a little bit more about those alternative names. In fact, starting with software number 5, that assignment, which you'll be able to do after I talk about what we need to talk about today. Well, starting with that assignment, you want to start using the alternative names for the registers instead of the X with the number. And the only other software assignment, because this is the last software assignment except for the software part of the final project. So for this software number 5, along with the software final project, you want to use the alternative names for the registers instead of the X and the number. Okay. So we'll talk a little bit about that. And then we're going to go into what assembly directives are. You'll see that these are instructions directly to the assembler. Okay, so it's not part of the program. And then really what the focus today is, and what the new thing you need to know in order to do software number 5 is how to put data into the data segment of the real memory. Remember that real memory has 3 segments to it. Right, there's the code segment. What goes in the code segment? What do you find in the code segment? The instructions. Right, the instructions, right? That's where the program is. That's what the instructions are. And then you have the data. And then on top of the data is the stack. We're not going to talk about the stack until a couple of weeks. In fact, that's the last lecture when we talk about the stack and subroutines in assembly. So we're going to see how you put data into this data segment as well as how you read from it. And just like the code segment of real memory, the data segment and also the stack segment, they're byte addressable. Okay, so just like we talked about the code segment, right? Each byte has an address in the data segment as well. I remember each row is 32 bits. And you got 4 bytes each row. I could keep on going. Now, remember, the first instruction is always at address 0. Okay, so the first instruction of our code segment, first address of our code segment, where the first instruction is, that's address 0. Does anyone know what the top address is in the code segment? Like what this range is? It goes from 0 to what?
0, 0, 0, 5 FFs.
Well, 5, 5, or 2, 5, or all zeros. Let's put all the zeros.
5 FFF.
Right.
The thing, the last one is for FFC.
Right. Yeah, I was going to say what you said first. That would be the last address of an instruction, but the range goes up to 5 FFF. So you got it. Okay. So that means that the data segment starts in 0, 0, 0, 0, 6,000 hex. Okay, remember these are all hex. Okay, so our data segment starts at 6,000 hex. Okay, so anyway, we'll come back to this and you'll see how it fits into when we get to you know, how you put things into the data segment, also when you read them. But like I said, let's start with just talking about a little bit more. We talked a little bit about the reg files, but not really about the alternative names and also their uses. I mean, one thing we did talk about is that there are 5 special registers. Right? Remember, one of those special registers is X0. What's the alternative name for X0? 0, 0. Right? Why do we call it the 0 register?
It's always zero.
It's always 0. Right? Right? Remember, we hardwired it to 0. How about register 1? What's its alternative name? You look on that sheet. RA, which stands for return address. Okay, how about register 2? That's P for stack pointer. Now, I'm just listing them here. We'll come back and see what the uses of these special registers are when we get to the stack and also subroutines. Okay. Now, there's also register 3 and register 4 that are specialty registers. I forget what they stand. What's register 3? It's like a global. Is that the global pointer? And then register 4 is like a thread something. Yeah, see, I don't remember those because we don't use them in this class. Okay, you may use those later on, but for our purposes, you can forget about them. Okay, then we have a bunch of registers that have the alternative name temporary. Okay, these temporary registers, and as the name implies, these registers do not store long-term data. So, do not store long-term data. Okay, so some examples where you would use a temporary register is like for a loop counter. And also like if you're using a register for immediate or intermediate, sorry. Intermediate on my mind here. Intermediate calculation. Okay, so you know, short-term types of stuff. So if you look on that handout, you look at the temporary. So like, for example, T0, that's register 5, that's your first temporary register. Then you have T1 and T2, which registers 10 through 7. Oh, down here, I'm looking at the wrong table. The bottom table, it shows you that we have 7 temporary registers, right? T0 through T6, and then it lists the actual registers, right? T0 would be register 5, T1 would be register 6, T2 would be register 7, T3 would be register 28. So you see that bottom table, it tells you what register goes with the alternative name. Okay, so save registers, well, that's just the opposite of temporary. This is where you would store long-term data. You know, so these are things like addresses, like input data. What else is there? Oh, results. Okay, so you know, data like that is what you would put in the save registers. And again, if you look at the handout, you can see that there's 12 save registers, S0 to S11. It also has what the corresponding, you know, alternative name is for the register, which is the number. Okay. Now, function arguments, there's registers that are labeled A that are used for these arguments. That comes up when we get the subroutine. Okay, so I'll just kind of mention it now, but we'll come back to this when we get to the subroutines. So really the whole purpose of having these alternative names to the registers is to give some like some standard to what registers are used for what. And that sort of makes it easier to make programs more mobile, right? Because if people are using the same registers to do the same types of things, it makes it easier when you transport the programs around. Okay. And like I said, starting with software number 5, start using these alternative names. Now, for software number 5, if you use a save for really what is temporary, and you use a temporary for really what's saved, you're not going to be marked down. Okay. Now, for your final project software, okay, there, since that involves a subroutine, you got to make sure that you're using the alternatives for the right purpose there, because you could get marked down for that. But for this assignment here, like I said, if you switch these, you're not going to be marked off for it. Okay, so any questions up to this point? This is mainly definition type of stuff. Okay, so let's get to assembly directives. So like I mentioned at the very beginning, an assembly directive, it's basically like telling the assembler to take some sort of action. And the important thing to realize about this is that an assembly directive, it's not an instruction. Okay, so it's not like an instruction that's in a program. Okay, because there is no machine code for an assembly directive. Okay? No machine code. Right. Remember, every instruction that's in our ISA, right, our instruction set architecture, every instruction has a machine code, right, a 32-bit machine code. Okay, but assembly directives do not. They're not like an instruction. Okay. So here are some of the assembly directives. This one here is a dot, okay, like a period. So dot EQ, sorry, my U's often look like, oh, wait a minute, no, it is a V. I'm sorry, this is a V. It's EQV. And what it stands for is equivalent. And here's an example where you're making the word switches equivalent to this number. So now, you know how we were using, let's write it over here. We're using load immediate and then a register, like X5, although now you would put the alternative name. What's the alternative name for X5? Either actually a better register to use would be a save register, because we're going to put an immediate that's an address, represents an address into here. So what would be a good, well, actually, we just put S0. What register does S0 correspond with? Register 8. So remember before you put like load immediate, but you have some X here because you didn't know it, or you weren't using the alternative name. And then you would put the number that was the switch address. Okay. Well, if you did this before you had this instruction, well, instead of putting the number, you could just put switches. All right. The reason you might want to do that is just to make the code a little bit more readable.
So RARs will understand it if I type out LIS0 switches.
As long as you did this before. See, the other thing is this dot text. This is a default. So if you don't put anything like what we've been doing, right? Because what you've been doing up to this point is you just started, when you typed into RARs, you just started with whatever your first instruction was. Okay, and that's all we had. See, all we had was instructions in the code set. So if all you have is instructions and you don't put anything, you don't put any assembly directive, it's just going to take what you have as code. Okay. Okay, so the dot text, that anything that follows the dot text is code. But if all you have is code, you don't have anything else, like you don't have anything going into the data segment, you know, like what we've been doing up to this point. Well, then you don't need it because it will default to it. But if you were gonna use this equip, you would put this along with this line here, and now you would put dot text so the assembler knows what follows its code. So then if you put this line after the dot text, it will make the equivalent. But without this ain't gonna work. Okay? Okay, and then, when you get to the data segment, okay, where you want to put data into this data segment of real memory, here's the assembler directive, it's just dot data. And the default is a word. Okay, so if you don't tell it how to treat that data, you know, whether to treat it as a word, a byte, or a half word, it will default to a word. But you can specify, if you want to specify either, you know, word, byte, or half word, you can specify it by just putting after dot data, putting either, you know, dot word, or dot byte, or dot half. And we're gonna do some examples coming up. Okay. All right, in fact, let's look at this example here. So we start off with assembly directive. Okay, so that tells, or it directs, I guess, the assembler to now treat what's after it as data that it's going to put into the data segment of real memory. So right here, this dot byte hex 23, this data would be at address hex 6000. Because whatever's first after the dot data assembly directive, it's going to put that at the first address of the data segment. So you see this byte would be at address, you know, all zeros, 6000 hex. Okay, so you see that hex 23 would be right in this byte right here. Okay, this next byte, the data 10, that would be at address 6001. Okay, so we have the 23 hex here at 6000. Then, you know, this is 6001, this is 6002, 6003, 4, 5, 6, 7, 9, 10, which is A, G, E, E, F, and what goes next here? After F. 1, 0, 1, 1. So you see this line here would put that hex 23 right in this byte, address 6000. Then this line here would put this data 10 in this byte, address 6001. Then this half word of hex 25 would go into address 2. Right, and since it's a half word, if we pick up these 2 bytes, then this word 100 would go into address 6004. And we'll pick up these 32 bits. Does that make sense? Any questions on that?
It won't complain if we break a line out, like if we do the half word at 03, then it'll just go 03, 04.
No, it's the same as within an instruction that you can't cross a word boundary.
Okay.
So yeah, if you try to put a half word with address 6003 where it tries to use these 2 bytes, it would complain. So yes, all these segments, whether it's the code segment, data segment, or even when you get to the stack segment, you can never cross a word boundary. And that's based on how the hardware is designed and how that memory model is designed. It doesn't allow that to happen. Okay, so you can also in the data segment, you can also use what we call symbols, which is just like a label in the code segment. Right? Remember in the code segment when we have like branches and jumps, we use labels for the intermediates. Well, in the data segment, it's the same sort of thing, but they call it a symbol instead of a label. Okay? So if we're going to use data segment symbols, again, you start off with the dot data that tells the assembler what's following is going to be in the data segment of the real memory. And then you see here, we're just using this symbol for this address. This would still be address 6000. Okay, like we talked about up here. This would be 6001. This would be 6002. And this would be 6004. Okay. Now you could have another label. Okay, like I have here, label 2. Okay. Now, what address would this byte be at? 6008, because since this is a word, right, it's taking up these 32 bits. So the next address available, right, without crossing a boundary or overwriting data we already have is this address here. So you see, this would be 6008. That make sense? Any questions? Everybody good? All right, now let's look at reading data. Okay, see, the assembler is going to put the data into the data segment, right? But now let's say we want to read from it. Okay. Well, here's an instruction you haven't seen yet. Okay, this is another load instruction. Okay, LA. So just like anytime you see a new instruction, you should go right to your instruction manual. Okay, and if you go to LA, it stands for load absolute address of symbol. And if you look at the form of the instruction, this is a destination register, and this is a symbol. Okay, again, symbol is like a label for the data section. Okay. So what this is going to do is this is going to load the address of this symbol into this register. So you see, this would load the address of this symbol. So it would load 00006000 hex into register 5. Okay. All right, and then after that, this is a load command you've seen before, right? This is a load byte. And if you look at the instruction again in the manual, you'll see this is a destination register. This is a source register. I think it's source 1. Doesn't really matter for what we're doing here, but just to be accurate, let's look at our manual. Yeah, it's source 1. Right, this is just an immediate, right? Just the value. So, I mean, you've seen this before, right? Because we've done like load words and store words where there's this number in front of a register. So what happens here? Like what happens with this one and what's inside the register?
Offset.
Right.
To the contents of X5.
Yeah, exactly. This just acts like an offset, right? So it just adds 1 to what's in the register of 5. If we put in this hex 6000 into 5 with the LA command, right? So it's going to take the contents of address 6001 and put it into register 6. So it would take this byte right here, this 20 hex. Okay, this would put 20 hex into register 6. All right, does that make sense? And are you getting used to this? Because you've seen this before, right? This isn't new. All right, so you see that's how you would read the data from the data segment. It's an LA followed by like either a load bit or a load word or a load half words, depending on what you're trying to get from the data segment. Okay. All right. Moving on. to do arrays in assembly, actually, I think I made a mistake here. Oh, no, I didn't. Sorry, it's good. I was thinking this should be space, but space should be down. So, when you create an array in assembly, you're using this dot space assembler directive. But you got to start with dot data again, because this is, anytime you're dealing with the data segment, you start with dot data. But what you can do with this dot space directive is you can allocate a portion of that data segment without initializing the values. See, like here, we're putting a value into these different addresses of the data segment. But you may have a case where you just want to, have a portion of your data segment ready to put some data in, but not necessarily initialize it with any data to begin with. Okay, like maybe you're going to come back later, like after a calculation or something, and then use a store command, put data into that address. Okay, so if you just want to define memory space without initializing this, a specific value, you can use this dot space. So see here, I have dot space 20, and I just chose a number here. This number is bytes. So, since this line is the line right after the dot data assembly directive, it's going to start at address 6000 because that's where the data segment starts. And it's going to allocate 20 bytes. So this byte, this byte, this byte, this byte, these 4 bytes, these 4 bytes, these 4 bytes, these 4 bytes. You see, these 20 bytes have been allocated by this one directive. Okay, but no initial values were put in. Now, the thing you got to remember is that there's going to be something there, right? Because there's always bits. It's not like, it's voided of bits. I mean, there's zeros and ones there. It's just that they haven't been specified to any value. Okay. Now, how many words is 20 bytes? 5. 5.
20 bytes is addresses, right?
Say that again.
So we're saying the 20 bytes we're talking about, that's in addresses, right? Not context.
Well, yeah, it's these spaces, if you will, right? It's byte addressable. So yeah, we're talking about 1, 2, 3, all the way up to here, 20 bytes that we've allocated. Each one has an address. Yeah, so we have 20 bytes, and since there's 4 bytes in a word, this would be 5 words. Okay. And what are going to be the 5 addresses of those 5 words?
1, 4.
Well, it always starts at address 6000. See, this is going to be the address of our first byte. Yeah, so this would be 6000, the first one. And then the second word. Yep, 6004, right? Because words are always separated by foreign address, right? It's the same as in the code segment. Your instructions are separated by foreign address, right? So then we got what after 6004? 6008, 6000C, 6010, right? That would be 16. Well, whatever this is plus 16. Okay. So this allocated space of 20 bytes is taking up these 5 word addresses, right? It's taking up these 5 rows in our picture here. So now this symbol, which I'm specifying a word of this data, what address would this be at? 6014. Right, it'd be 6014. Right, because this word with address 6010 takes up these 4 bytes. Right, so you get this word address, right, 6014 for this data. So it would put this word, right, hex 10, it would put that in 14. So, you know, it would take up these 4 bytes. Okay, and then what address would this be at? See, I'm using another symbol and I'm specifying that I want this byte of this value. Right, it's coming after this. And what address would this be? Yep, be 6018. Right, does everybody see how I'm getting these addresses? Because that's really the key of understanding what's going on in this data segment, because you know, when you're defining, whether you're defining allocating space without a specified value or actually putting in a specified value into the data segment, you have to understand how the addresses work. Then also when you're reading from the data segment, you got to understand how the addresses work. Okay, that's the key to this whole thing. Okay, so everybody see what I'm doing here? It all gets back to what byte addressable means, right? It just means every byte has an address. And you just got to remember you can't cross word boundaries, right? So that's why the word addresses are always these furthest to the right that are different by 4, right? Because if they weren't, if you tried to use any of these other bytes as a word address, you would cross a word boundary. Okay, well, the last thing before we get to what you need to do for software 5 is just showing you how to create an array and then load from that array. And again, I'm just using an example here. So again, you start off with the data directive. Right? Again, this is going to be going into the data segment of real language. And then here I start with the symbol array. And again, I'm allocating 20 bytes. Yeah, so again, this is going to be like we have over there. I'm just redrawing it. Okay, it's going to start at 6,000. You know, 1, 2, 3, like we've been doing. Right, 6,004, 6,008, 6,000, 6,000. Right, so, and again, it's not specifying any values, so yeah, it's just allocated space. Okay, then I have another symbol I'm calling array 2. You can see here I'm defining or specifying 3 bytes. Now, this is something you can do in RARs. You don't have to put it all like here. You know, I put 2 lines. You could put this all on 1 line. Okay, just by as long as it's the same, you know, either byte, half word, or word. You can just use commas and separate them instead of doing a dot byte, you know, like I was doing over there. So what this would do is this would put data 3 into address 1. It's coming after this, so this has been allotted. So what's going to be the next address after this? You guess this? 60 what?
650.
Close, because this would be 6,011, 6,012, 6,013. Yeah, so yeah, this would be 6,004. There we go. See, that 3 would go in this byte right here. 6,004. And then 7 would go into the next byte address. Right? So this would be in 6,050. And then the 8 we go into address 6016. That makes sense? Okay, so like I mentioned before, when you're dealing with the data segment, and then you're gonna write a program, right, to do something with that data segment, you have to use this .text assembler directly, because that tells the assembler what follows our instructions. And again, you weren't doing this prior to this assignment because you didn't have to, because all you had was code. Okay, but if you've got some other segment you're dealing with, like this data segment, you have to tell the assembler where your instruction starts. Okay? Or where your program starts. And you can see here, our first instruction is load absolute address. So it's going to take the address of this symbol. Again, this is the symbol. This is the destination register. So it's going to take the address of symbol array 2 and put it into register S0. Put it into register S0. So array 2, like we said, its first address here is 6014. So you see, it would put 6014 into register S0. Okay, and then this LA command would take the address of symbol array and put it into register S1. Right, so array, you know, that was the array that we just allocated space, didn't put any specified values into, but it would have address 6000. So this would put 6000 into, well, hex 6000 into register S1. Okay, so then now we're reading from the array. So we've got a load byte. This is the destination register, P0. Again, that's immediate. And this is a source register, RS1. And so we already put the address of array 2 into this register S0. So what do you think is going to happen? What is this instruction going to do here, this load byte instruction?
So the second byte in the add array 2.
Right, so what data is it going to put into register T0? I mean, you're right, for what actual data? 7. Yeah, see, because remember how this works again. It's going to take this immediate, add it to what's in this register. We put the address of array 2, right, which is this 6014. We put that into S0. So it's going to add 1 to this address 6014, make that 6015. Take the data from that address and put it into this register, right? So this data is at 6014. This data is at 6015. So you see, this is going to put 7 into register T0. Does everybody see that? Okay, what's this instruction here, this load word gonna do? What did we put into S1? Put in this address, right? We put in address 6000. So what's it going to do with that address of 6000 in this key? Offset. It's going to offset. So now we have an address of 6008, and it's going to load whatever word we have at that address into P1. Now we didn't specify anything, so who knows what it's going to be, right? But that's what it would do. Whatever is at this word address, it would take it and put it into register T. Does that make sense? Okay, well, if that all made sense, then what you need to do for software number 5 will hopefully make sense also. Now, in previous software assignments, I would always do one of the examples. Let's see, where's my, oh, I would do one of the examples in class and I'd have you do the second one. This is a little bit different. I'm not going to do number 2. The reason I'm not going to do number 2 of this assignment is because number 2 is basically a sorting exercise. And really, in my opinion, it creates an uneven playing field for the class, because when doing this particular problem, you really have to look at like a sorting example in another language, and preferably C. Like people that know C language, you could basically take any sort of sorting algorithm from C and translate it into assembly. It's not real easy, but it's easier than trying to do it from scratch. Trying to do a sorting algorithm from scratch is not an easy process, like to come up with the flowchart from scratch. And because some people know C and some people don't know C coming into the class, I just don't even bother with that second part of the problem. So what I'm going to do instead is I'm going to get you started on part 1, the same part that you have to turn in. And how I'm going to get you started is just show you how you set up the data segment. Okay, because if you look at the problem here, you're going to put a sequence. I had to look this up to see how the name was pronounced. It's the name of an Italian mathematician. Does anyone know how to pronounce it? Say it again. Oh, so this is like this. So it's like this. Fibonacci. Okay, because when I looked on Google, it had this. But it's Fibonacci. Okay, well, thank you for using that. Oh. Well, anyway, there's this sequence, and I guess it'll just go on forever, where you start with 0. So you go 0, 1, 1, and then to keep going, you just add the 2 like most recent values. So, like for example, 0, 1, you add the 0 and the 1, you get 1, and 1 plus 1 is 2, then 1 plus 2 is 3, then 2 plus 3 is 5, 3 plus 5 is 8, and so on. Okay, that's how the sequence works. And supposedly this has applications in like computer science and like business world and all kinds of different things. But first I ever heard of it was when I looked at this problem. I've never heard of it before. So anyway, we're taking this sequence. You want to start at 0, and it will go all the way up to this number here, 46,000 change. And you're going to have 25 values. So go from 0 to this value using this method that I just talked about, where you add the last 2 numbers to get the next number, and you just keep going like that. Well, there's going to be 25 values. So you want to put these 25 values into the data segment. And then you want to write a program that progresses through the array. So it progresses through the data segment. And it takes the difference between values that are 3 spots away. And then it outputs that difference to the LEDs. Okay. So I'll get you started on how you put the data into the data segment, and then you got to write the program to do what it's asking. Okay, so to put the array into the data segment, you would just start with the directive, the data directive. Okay, so we got data, and then now symbols, just like labels, you can put anything for a symbol, just like a label, right? And you want to make your symbols in the data segment descriptive, just like your labels in the code segment. So what I did here is I used the symbol sequence that's what the data is gonna represent. Right, so you put dot data, you put a symbol, and I just made all these values words. And then you just start listing. So you have 0, 1, 1, and 2, 3, 5, 8, and 13, and then you just keep going until you reach this 46,368. You know, go ahead and put these numbers in, and if you do it in your head or use a calculator, check, like I would Google it and then check to make sure that you have all the right values before you go ahead and write the program. So you see, that's all you need to do to put the data into the data segment. And then you got to tell the assembler where the code starts. So after this, you would just put dot text, and now you put your assembly language instructions for your program after that, like you've been doing. Okay, so the only thing that's new is how you get the data into the data segment. You know, now you got to figure out how to go through the array and take the difference of the values that are 3 spots away. And then you got to output each difference to this output of the LEDs. Okay? So is it clear? Now, you can read the problem statement yourself. It's on campus. But is it clear what has to be done?
Find the difference between 3 spots away.
Right, right. Until you get to a point where there isn't a value, then you would stop. But yeah, it's like, you know, first you would start with this and 3 spots away. So it'd be like the difference between 0 and 2, then the difference between 1 and 3, and then 1 and 5, 2 and 8, and so on. And then you just want to output the difference. Like you find the difference, output, find the next difference, output, find the next difference, output. So what does that sound like? What kind of construct? Yeah, you're gonna have some sort of loop. All right, so now this is due next week, and that's because, remember, because of the midterm, I delayed the due dates of the hardware assignments you had last week. So the ALU and the immediate generator, that's due tomorrow. So if you haven't got that done, that's what you should work on first. And then the branch condition generator and the branch address generator, that's due this Friday. And this is due Tuesday because Monday's a holiday. Right? Monday's President's Day, so that's why it's due Tuesday instead of Monday. Okay, and then also very important, and I mentioned this in the email that I sent. Next class, okay, so this Thursday, you know, we're going to talk about the control unit. We're going to start talking about the control unit. That's a very important class. Now, all classes are important, but in particular, the control unit is important. That's probably the most challenging, well, more than probably, it is the most challenging hardware module that you need to design. Okay, that's why we're taking 2 classes on. Well, the beginning of that class, I have a graded class activity. Okay, so you want to make sure you're here at the beginning because you have to be physically present to get credit for an activity, an in-class activity. Okay, you know, the last in-class activity we had, it was after I had talked a while, you know, like maybe an hour or so. But this is right at the beginning of class. Okay, so just like today, everybody was on time. Amazing how a midterm will do that, right? Well, you should pretend there's a midterm every day, so you're always on time every day. I mean, you've heard that old adage, right, about when you go for a job interview or your first day of work, or even if you plan to work somewhere for a long time, that old, if you're 15 minutes early, you're on time. If you're on time, you're late. If you're 15 minutes late, you're fired. You've all heard that one? Although, I don't know, a lot of companies now are very lax on when you show up for work. So that may not be as true as it once was, but at least that's what I was always told when I was an undergrad, so it's stuck in my head. Okay, so anyway, you get the rest of the class time to work on whatever you need to work on.